Exactly. So I'm a PhD candidate at Leiden Observatory, and I'm working with Joe Hinawi, who already just introduced you to our pipeline, so I can directly dive in. And one sentence summarized what our pipeline is doing. So given an observed quasar spectrum, we are jointly fitting for the quasar continuum as well as the IGM damping wing imprint, and what we get out is the full posterior distribution on global IGM neutral fraction, quasar lifetime, and a bunch of quasar continuum parameters that we can directly marginalize over. And what I would like to talk about first is the precision at which we can actually constrain reionization with this. And for that, let's take a look at the marginal XH1 posterior as a measure of the uncertainty, this 1 sigma region of the XH1 posterior as a measure of the uncertainty on this quantity. And if we now perform the inference on a whole set of MOG spectra at different points in astrophysical parameter space, we can see how this uncertainty varies as a function of the true value of XH1 itself as well as the lifetime of the quasar. And as you can see, there's quite a lot of variation, basically getting better the longer, the shorter the lifetime of the quasar and the more neutral the universe is. So basically, the stronger the IGM damping wing gets, as you can see on these simulated IGM transmission skewers. And we infer XH1 at a median precision of around 28%, where half of this error budget is due to the continuum reconstruction process, and the other half just due to the stochastic nature of ionized bubble sizes during reionization, which you can also see in this scatter here, red dot of the Lyman alpha line in these transmission skewers, which raises the question, what quantity are we actually measuring if half our error budget is just due to the stochastic nature of reionization itself? And to answer that, let's take a look at two different quasars at the same redshift, so same global IGM neutral fraction. But as you can see, the light from the first one only passes through black, already ionized regions, whereas the light from the second one still encounters many neutral patches. So as a result, only the second one has a clear damping wing imprint. And as it turns out, we can instead define a certain H1 column density with a specific weighting function that exactly mimics this Lorentzian cross-section that shows up in the full optical depth integral that gives rise to the damping wing imprint in the first place. So if we order everything according to this new summary statistic instead of the global IGM neutral fraction, it turns out that we can basically eliminate all the scatter red dot of the Lyman alpha line. So we have a very tight parameterization of the IGM damping wing now. And of course, we can also perform the full inference now with respect to this new local label, and this is what I'm doing here. So it turns out that we can actually infer this local H1 column density up to a median precision of around 0.7 dex. Again, the better, the stronger the damping wing imprint gets. And I can also show you this on the observed JWST spectrum that Joe already just showed you. So instead of inferring the global H1 value, we even get the information about the local H1 content in front of this quasar. And of course, in the end, we can also convert this back to a constraint on the global IGM neutral fraction. I'm not allowed to show this here, but please subscribe. And in the last minute, I would like to switch gears a bit and talk about what we can actually achieve in the coming years thanks to Euclid, because this was only one single spectrum, and we already know many more quasars at high redshift, and Euclid is going to increase this number by up to a full order of magnitude with its wide field survey in the coming years, which we can, of course, all use for damping wing analysis, so assuming that we can get spectra either from the ground or from JWST. And just assuming a very simple reionization history and a lifetime distribution consistent with recent measurements, I can generate a MOG spectrum for every single one of these objects and perform the inference on those. And these are the combined constraints that we get if we group them into redshift bins and multiply the resulting XH1 posteriors. And this is the plot you just saw in the beginning. So if we now put everything, all the combined constraints onto this plot, you can see that we can expect very exciting constraints on reionization thanks to JWST and Euclid in the coming years. Thanks.
Thank you.